So we were talking about maximal ideals and prime ideals, and I want to continue, but I want to pause a little bit and have a little interlude on polynomials in multiple variable. We'll need this to give some examples of maximal ideals and prime ideals. If you just stick to one variable polynomial ring, then I don't think you see the full picture. So that's the reason for this interlude. I realized I need to know a little bit about this to give examples of the kind of ideals that we want to look at. In particular, I want to talk about one lemma which tells you how to construct homomorphisms from multiple variable polynomial ring. So I think you've seen multiple variable polynomials in multiple variable calculus class. So up here on the right, for example, there's a polynomial in two variables, x and y. I call it fxy. It's an expression that looks like 2 minus 5y plus 3x squared plus etc. So a general polynomial in n variables, x1, x2, xn, with coefficients in a ring R, is a creature that looks like this. There are some numbers, or rather some elements of the ring R, and then multiplied by x1 to the power something, x2 to the power something, xn to the power something, where these somethings, I1, I2, In, are non-negative integers. And it's really a finite expression. So let's be precise. Let R be a commutative ring with R. Commutative ring with 1. So R will be the ring of coefficients. That's where these guys are going to come from. And this is going to be my notation R, x1, x2, xn. It's going to be the set of all polynomial in n variable x1, x2, xn with coefficients in R. A typical element, an element f in R, x1, x2, xn has the form this, where these things are in R and only finitely many of these coefficients. It's convenient to write it this way, but we let it vary over all non-negative integers, but of course it's a finite expression. It doesn't go on forever. So only finitely many of these are non-zero. Okay. So up on the right, in this example, this is an element of Rxy. The coefficients are real number, and the two variables are called x and y. If you don't want to think of real coefficients, you can just think of integer coefficients. The coefficients are even integers. Yeah. These kind of polynomials, the simplest kind, x1 to the power something, x to the power something, these are called monomials. So that one is a monomial of degree I1 plus In. So for example, here is a monomial of degree 3 plus 1, 4. X cubed times y. Once you define degree of a monomial, you can define degree of a polynomial. Degree of a polynomial is the maximum of the degrees of the monomials that occur in F with non-zero coefficient. So our example here, this F has a degree 4, right? So here are 2 degree 4 terms, and that's the biggest you get. These are degree 2 terms, etc. Okay, so you can define degree of a polynomial, and once you have that, you have this basic fact that if the coefficient ring is a domain, then the degree of the product is sum of the degrees, and if R is a domain. And also, maybe I should write it on the left side. Assume R is a domain and f g in Rx1, x2, xn, then degree of the product is the sum of the degrees, and also Rx1, x2, xn, it's itself a domain, if R is a domain. So that's a little lemma that works just the same like first variable, one variable polynomial ring. What fails in multi-variable polynomial is that you don't have such a nice clean-cut division algorithm. The division algorithm does generalize, but in a much more subtle way, and it's rather delicate. But this much you do. I did not quite say formally what multiple variable polynomial rings are. We spent quite some time defining what Rx1, one variable polynomial, means. This has been defined formally, carefully. One way to define two variable polynomial ring is to say that a two variable polynomial is nothing but a one variable polynomial in x2 where the coefficients are again one variable polynomial in x1, like I have written up here. See, this two variable polynomial can be written as a one variable polynomial in y where the coefficients are themselves one variable polynomial in x. Right, so if I can make a little space here. Oops. This is, you can say this is f0 times x plus f1 of x times y plus f2 x times y squared, where f0x is this thing, f1x is that thing, and f2x is that thing. So it's a polynomial in y, where the coefficients are again polynomial in x. So you can call this one a1, and then this one a2 is nothing but a1 x2. And then similarly you can say rx1 x2 x3 is a2 x3, etc. So you can make an inductive definition like this. The advantage of this is that now I can use the one variable polynomial facts. Facts like, so this thing, if R is a domain, then n variable polynomial ring is a domain. That follows from the one variable fact. Because R is a domain, this is Rx1 is a domain. Now that A1 is a domain, this is a domain, so A2 is a domain. Now that A2 is a domain, this is a domain, so A3 is a domain, etc. So this one immediately follows. And we know that there is a ring structure because they are all really polynomial ring in one variable. So we still have to write down this little lemma which tells you how to make homomorphisms from these polynomial rings. We'll do that